Okay, so let's resume our lecture of chapter 6, and this time we're going to focus on stoichiometry. So fundamentally, when we think about chemical reactions, they require a specific whole number ratio of reactants for a complete reaction. Further, a whole number amount of product molecules are produced based on the chemical equation. So to help us visualize this, let's use a very simplistic example. Suppose you're trying to make a sandwich based on a recipe, and it requires 2 pieces of bread, okay, and 3 pieces of cheese. And from this relationship, if we mix 2 pieces of bread and 3 pieces of cheese, we get 1 sandwich. Okay, we've probably done this throughout our lives. We've probably cooked food based on a recipe that requires a specific number of each ingredient. Okay, so let's try to generate some relationships between each of our ingredients. So for example, for every 2 pieces of bread, how many pieces of cheese do we need? So how much cheese do we need per 2 bread? What is our cheese to bread ratio? So for 2 pieces of bread, how many pieces of cheese do we need? And don't worry, this example will have a payoff with respect to chemistry. And don't be shy to unmute and propose your responses or to type your responses in the chat. 3, right? We see from our recipe, we need 3 pieces of cheese per every 2 pieces of bread. Okay. Now let's look at a product relationship. How many sandwiches do we make per every 2 pieces of bread? How many sandwiches would we get if I only have 2 pieces of bread? 1, exactly. We have 1 sandwich per every 2 pieces of bread. This is a product relationship. Okay. Now, just for completeness sake, for 3 pieces of cheese, how many sandwiches do we make? So this time, for every 3 pieces of cheese, my question to everyone is, how many sandwiches do we get? How many sandwiches do we get if I use 3 pieces of cheese? One, exactly. It's a 1 to 3 ratio. Okay, so let's take this one step further. We are able to generate each of these ratios, which we like to call a stoichiometric ratio. And the stoichiometric ratio provides us a relationship between the moles of one species in a chemical reaction and the moles of another species in that same chemical reaction. Okay, so we can apply these ratios, and this recipe, critically, just like a chemical equation, has a distinct stoichiometric ratio of reactants and products based on the reaction coefficient. So these numbers in front of each of our reactants and products are really critical. And we can use this stoichiometric ratio to perform calculations. So let's suppose we have the same recipe and we start with 4 pieces of bread. How many pieces of cheese do we need to completely use up our bread? So we're going from bread to cheese as our unit conversion map. Okay, so if I start with 4 pieces of bread, let's try to make a ratio. Let's try to read off a ratio. So just to draw another picture, just to help us see this pictorially for those who like seeing reaction pictures. I always find drawing a picture of the number of reactants and products helps me keep things organized. So my question to everyone is, if we have 4 pieces of bread and we're converting to cheese, the units of cheese will be on top. The units of bread will be on bottom. Now, looking at our recipe, how many pieces of cheese do we need per how many pieces of bread? What's our cheese to bread ratio? What's our stoichiometric ratio? It's 3 to 2. We need 3 pieces of cheese per every 2 pieces of bread. Units of bread cancel, and we're left with 6 pieces of cheese. Okay, so we've used our stoichiometric ratio to perform a particle-to-particle conversion. We've converted from the amount of a reactant to the amount of another reactant. So this sort of reminds us a little bit of our mole-to-mole conversions that we did using the formula ratio. Okay, now if we start with 9 pieces of cheese, how many sandwiches can we make? Okay, this time we're going from cheese to sandwiches. Okay, so starting off with 9 cheese, we're converting to sandwiches, so sandwiches are on top. So how many sandwiches do we get per how many pieces of cheese? What is our stoichiometric ratio? What is our sandwich to cheese ratio? Looking at our picture, 1 to 3. We get 1 sandwich per every 3 pieces of cheese. That in turn gives us 3 sandwiches. Okay, so we can also convert between mole or particles or the amount of a reactant and the amount of a product. Okay, now, it may appear like we're suddenly shifting gears and tackling an entirely unrelated equation, but let's pay attention to what we've talked about, and let's try to apply stoichiometry to a chemical equation that is related to our bread and cheese example. If you want, you can think of iron as our bread. So we have two atoms of iron. For chlorine, we have 3 molecules of chlorine reacting to make 1 molecule of iron, this iron 3 chloride dimer. Okay, so let's try to answer these questions that are built very similarly to our bread and cheese example. So first, how many molecules of chlorine gas are required for complete reaction of 2 atoms of iron? So how many molecules of chlorine are required for every 2 atoms of iron? So how many molecules of chlorine do we need to react with 2 atoms of iron? Looking at our equation, we see we need 3 molecules of chlorine per every 2 atoms of iron. Perfect. We can also write this as a mole ratio. We need 3 moles of chlorine per every 2 moles of iron. Okay, now let's do a conversion between reactants and products. So how many moles of the following species are produced for every 2 atoms of iron that react? So we're looking at molecules of Fe2Cl6 for every 2 atoms of iron. So how many product molecules do we make for every 2 atoms of iron? Yep, so the ratio is 1 to 2. We get 1 molecule of product per every 2 atoms of iron that react. And again, we can write this atom to molecule ratio as a mole ratio. So we get 1 mole of product for every 2 moles of iron. Does the parallel make sense to everyone so far? Is everyone starting to see what we're doing in terms of stoichiometric ratios? So just like making a sandwich, we're looking at how many molecules of each reactant do we need for a complete reaction, and the ratio is based on our recipe, based on our chemical equation. Okay, now let's try to apply this to let's try to continue on with this. How many molecules of product are produced for every 3 molecules of chlorine? So we're looking at molecules of product for every 3 chlorine molecules. So what is our molecule to molecule ratio? So how many molecules of product do we make for every 3 chlorine molecules? It's 1 to 3. We get 1 molecule of product, as we can see in our chemical equation, for every 3 molecules of chlorine. Okay, continuing on, if we start with 4 atoms of iron, how many molecules of chlorine are required? Okay, so we're trying to go from atoms of iron to molecules of chlorine. So if we start with 4 atoms of iron, just thinking about conversion logic, if we're going from atoms of iron to molecules of chlorine needs to be on top. In order to cancel atoms of iron needs to be on the bottom of our stoichiometric ratio. And would someone looking at the chemical equation like to tell me what is the ratio of molecules of chlorine to atoms of iron? What is our ratio? If we go up and look at our chemical equation, what is the ratio of chlorine to iron? What is the ratio of chlorine to iron? And I see in the chat, wonderfully, 3 to 2 is exactly right. We have 3 molecules of chlorine per 2 atoms of iron. We're just reading off the coefficients. So atoms of iron cancels, and we're left with 6 molecules of chlorine. Does this example look familiar to everyone? Does this remind us of anything that we just did? This exact calculation, 4 times 3 over 2. We actually did this calculation before in our bread and cheese example. Okay, let's now try to answer the next question. How many molecules of product are produced when 9 molecules of chlorine react? So we're starting with molecules of chlorine, and we're trying to convert to molecules of product. So we have 9 molecules of chlorine. And my question to all of you is, how many molecules of product are produced per how many molecules of chlorine consumed? What's our mole to mole ratio? What's our ratio of product to chlorine? Oops, let me zoom in a little bit. So what's our ratio of product to chlorine? 1 to 3. Where did we get our 1 to 3 ratio from? If we look at our chemical equation, we have 1 molecule of product for every 3 molecules of chlorine. Okay, and that in turn gives us 3 molecules of product. Any questions so far? Does this concept of stoichiometric ratios make sense to everyone so far? Did the bread and cheese example help make this idea a little bit more tangible? Any questions on this example? So if I don't see any other questions in the chat, let's really try to draw parallels with our previous knowledge. So mole ratios in chemistry come in two major categories: an element or ion mole ratio. These are within a single substance. This is often called the quote unquote formula ratio. So for example, in P4O10, we know we have a certain number of moles of phosphorus per mole of oxygen. In this case, reading off our subscripts, so we're looking at our subscripts. In this case, we have 4 moles of phosphorus per 10 mole of oxygen. We also know that we have 4 moles of phosphorus for every 1 mole of P4O10. And we also know we have 10 moles of oxygen for every 1 mole of P4O10. Perfect. So now that we have that set up, we've written out all of our mole-to-mole ratios for the following formula. Just the same way, for example, if we have potassium sulfide, we can say we have 2 moles of potassium for every 1 mole of potassium sulfide. This time we're looking at an ion ratio. We also know we have 1 mole of sulfide for every 1 mole of potassium sulfide. And then to finish off our mole-to-mole ratios, we know that we have 2 moles of potassium for every 1 mole of sulfide. Wonderful. So we've certainly used and we've written out mole ratios based on the formula. Critically, we are reading the subscripts. Now, chemical equations are really wonderful in that they provide a relationship between the number of reactant and the number of product molecules. Further, this particle-to-particle ratio can be written as a mole-to-mole ratio. So chemical equations also provide a relationship between the moles of a reactant and the moles of a product or another reactant, okay? So the stoichiometric mole ratio focuses, rather than on the subscripts, it focuses on these numbers in front. It focuses on our coefficient. Okay, so just like the examples that we've dealt with before, let's write some ratios. So for example, how many moles of water are required to react with how many moles of P4O10? What's our mole ratio of water to P4O10? And just read off the coefficients. That's all you're doing. You're just reading off the coefficients. So what's the mole ratio of water to P4O10? 6 to 1, exactly right. We have 6 moles of water per every 1 mole of P4O10. Okay, now let's look, what is our mole ratio of the moles of phosphoric acid per mole of P4O10? So how many moles of phosphoric acid do we make for how many moles of P4O10 that we consume? What's our mole-to-mole ratio?
4 to 1.
Yep, exactly right, 4 to 1. Now let's do one more, and let's ask how many moles of water are required to generate a certain number of moles of phosphoric acid. What is our mole-to-mole ratio of water to phosphoric acid? What is our mole-to-mole ratio?
6 to 4.
Yep, 6 to 4. Wonderful. So we can write out a range of mole-to-mole ratios by reading off our reaction coefficients. From this, we can apply our skill of mole-to-mole conversions from previous chapters in order to convert between moles of a reactant to moles of product and moles of a reactant to the moles of another reactant. Okay, so let's show how we can leverage this. So let's suppose we're given the equation nitrogen and hydrogen gas react to yield ammonia. I've already done everyone the favor of providing the chemical equation that is balanced. And before we actually look at the contents of the problem, I always like to list the potential mole ratios that I can use. So how many moles of nitrogen do we have for every mole of hydrogen? What is our ratio of nitrogen to hydrogen in this chemical equation? What is our ratio of nitrogen to hydrogen? 1 to 3, yep. We can also write this as 3 moles of hydrogen for every 1 mole of nitrogen. These ratios can be flipped. Okay, let's look at the ratio of moles of ammonia per mole of hydrogen. What is our ratio of ammonia to hydrogen? Two moles of ammonia per every 3 moles of hydrogen. And then finally, what's our ratio of moles of ammonia to moles of nitrogen? What's our mole to mole ratio of ammonia to nitrogen? Ammonia to nitrogen. 2 to 1. Yep, perfect. So as you can see, looking at a chemical equation, we can generate a plethora of mole to mole ratios. Now it's our job to selectively pick the mole to mole ratio that would help us solve this problem. So looking at our examples, we're asked how many moles of hydrogen are required to react with 6 moles of nitrogen. Okay, so starting off, we're going with 6 moles of nitrogen, and we want to convert to moles of hydrogen. Okay, so if we have 6 moles of nitrogen, if we're converting to moles of hydrogen, we're going to want moles of hydrogen on top and moles of nitrogen on the bottom to cancel. Okay, now let's fill in our coefficients. So how many moles of hydrogen do we need per how many moles of nitrogen? What's our ratio of hydrogen to nitrogen in this chemical equation? 3 to 1. We need 3 moles of hydrogen for every 1 mole of nitrogen. And that in turn gives us 18 moles of hydrogen. Notice that our units cancel. Okay, let's keep going now. Let's ask the question, how many moles of ammonia are produced when 3 moles of nitrogen react? So we're going from moles of nitrogen to moles of ammonia. If we start with 3 moles of nitrogen, how many moles of ammonia do we produce per mole of nitrogen? What's our ratio of ammonia to nitrogen? Looking at our equation, what's the ratio of ammonia to nitrogen? 2 to 1, exactly right. We have 2 moles of ammonia per every 1 mole of nitrogen consumed, and that gives us 6 moles of nitrogen. Okay, let's look at another example. We're asked how many moles of hydrogen are required to produce 4 moles of ammonia. So this time we're going from moles of ammonia to moles of, sorry about that, whoops, to moles of hydrogen. Okay, so we have 4 moles of ammonia. And my question is, how many moles of hydrogen do we need per mole of ammonia? So let's zoom up and let's look at our equation. So how many moles of hydrogen do we need per mole of ammonia that we make? What's our hydrogen to ammonia ratio? What's our hydrogen to ammonia ratio? What's our ratio of hydrogen
3
to
to 2.
ammonia? What was that? Oh, could you repeat that, please?
3 to 2.
Yep, exactly right. So we have 3 moles of hydrogen per 2 moles of ammonia. Moles of ammonia cancels, and that gives us 6 moles of hydrogen. Does this example make sense to everyone so far? Any questions on this example so far? Okay, so let's try to apply what we've learned. And for this problem, you can submit your responses in the chat verbally or via Canvas quiz 6.6. All the Canvas quizzes for this chapter are up and functional. So if you want to submit your responses for immediate feedback, you're welcome to do it via Canvas in addition to the chat. And I'd like you, given the following chemical equation, to answer the following 3 questions. So how many moles of oxygen are required to react with 5 moles of carbon dioxide? How many moles of carbon dioxide are produced when 4 moles of oxygen react? And how many moles of carbon monoxide are required to produce 6 moles of carbon dioxide? So I'm just going to pan up so that way you can see the equation. Note there are 3 questions in this problem solving set in the notes. We'll spend about 5 to 6 minutes on this example. If you have any questions at all, really do not hesitate to ask or unmute and ask your questions verbally, or you can ask your questions in the chat, and I'd be happy to provide feedback on your individual responses whenever they're submitted. So let's take a few minutes, about 5 to 6 minutes, to work through this example, and we'll come together as a group to discuss. And I'd like to see some responses via Canvas or in the chat, just so that way I can see everyone's comfortable with these mole to mole conversions. And again, if you have any questions at all, don't hesitate to ask. And if you have any proposed responses, don't be shy to message me with your proposed response for any of these questions. Checking Canvas. I already see a large pool of reasonable responses so far. Let's take another 3 to 4 minutes to work through this problem, and I'd like to see almost the whole class responding. And thank you again for those who submitted their responses. It's really helpful for me to get a sense of where everyone's at with the material. And the responses I see in the chat so far look perfect. So thank you again for submitting responses via Canvas. I see a lot of reasonable responses so far. So let's discuss this example together as a group, as almost the entire class has responded. So we're asked how many moles of oxygen are required to react with 5 moles of carbon monoxide. So we're going from moles of carbon monoxide to moles of oxygen. So we have 5 moles of carbon monoxide, and how many moles of oxygen do we need per mole of carbon monoxide? What's our mole to mole ratio? What's our mole to mole ratio in this case?
1 to 2.
1 to 2, exactly right. So reading from our coefficients, we have 1 mole of oxygen required per every 2 moles of carbon monoxide. That in turn gives us 2.5 moles of oxygen. Does this make sense to everyone so far? Okay, let's look at this next example. How many moles of carbon dioxide are produced when 4 moles of oxygen react? So we're going from moles of oxygen to moles of carbon dioxide. Okay, so starting off with 4 moles of oxygen, now let's ask the question, how many moles of carbon dioxide are produced per mole of oxygen? What is our ratio? What is our mole to mole ratio of carbon dioxide to oxygen? What's our ratio of carbon dioxide to oxygen? 2 to 1. So multiplying it out, we get 8 moles of CO2. And I corrected the Canvas quiz to reflect that. Does this second example make sense? Is everyone more comfortable with this second example now? Any questions on this second example? Any questions on this second problem? I noticed looking at the quiz analytics that this one was a little bit tricky, and I just want to make sure if there are any questions, we can get those addressed. Does that make sense to everyone? Can I get some confirmation in the chat that this makes sense to everyone so far? Yeah, I corrected the key for that one. So Canvas should be marking it correctly now. I made sure it's corrected. So when you reattempt it, it should not give you that weird error. Let's keep going with this next example. We're asked how many moles of carbon monoxide are required to produce 6 moles of carbon dioxide. So we're going from moles of carbon dioxide to moles of carbon monoxide. So starting off with 6 moles of carbon dioxide, how many moles of carbon monoxide do we need to produce how many moles of carbon dioxide? What's our mole to mole ratio? So looking at our equation, what's our ratio of carbon monoxide to carbon dioxide? 2 to 2. And that in turn, after the moles of carbon dioxide cancels, we get 6 moles of carbon monoxide. Does this example make sense to everyone? Perfect. Any other questions on these examples? If not, let's start integrating stoichiometry with mass mole conversions. So remember how I showed you this chart to go from moles to particles, grams? Well, I've now added all of the components that we've learned from chapters 3, 4, 5, and 6 together to make this nice little conversion chart to help you organize your thoughts and procedurally go through unit conversions. So fundamentally, the chemical equation provides a relationship between the moles of each reactant and product in the chemical equation. We can use Avogadro's number, molarity, and molar mass to calculate the particles, mass, or volume of reactant or product, okay? So fundamentally, if you want to deal with a chemical equation, if you want to use a chemical equation or a formula, you need to be in units of moles. Once you have units of moles, you can go to grams, particles, or volume using all the different conversion factors that we've learned. So in terms of the procedure that I want you to follow, I want you to balance the chemical equation. That's the first thing on the agenda. Your unit conversions won't work unless you have a balanced equation. Identify your starting units, and to use the chemical equation, again, you need to convert to moles. That should be your first goal in any stoichiometry problem. Now, just to showcase all the different conversion factors, to convert between mass and moles, you use your molar mass or molecular weight. To convert from atoms or molecules and moles, you use Avogadro's number. This one's a little bit interesting. If you want to convert between moles of a molecule and the moles of an atom of an element in that molecule, you use the chemical formula mole ratio, which is obtained from your subscripts. And finally, if you want to convert between the volume of a solution and the moles of compound in the solution, you use molarity. That's where this volume term comes from. We can relate the moles of a chemical species to the volume of solution containing that chemical species using molarity. So as you can see, this chapter really presents an opportunity to use all the different conversion factors that we've talked about throughout this course in order to calculate, starting with a certain quantity of material, how much product do we make, and how much other material is required for a complete reaction. So this is really powerful stuff. Now, this is nice and all, but let's show how we can apply this. So now, when you have moles, looking at this interface here between moles of known and moles of unknown. Again, in all cases, if you want to convert between moles of one species in a chemical reaction and another species in a chemical reaction, you have to use your chemical equation mole ratio, which is only obtainable from a balanced chemical equation. So, I can't stress this enough. Balance your equations. Okay, so let's give an example. Things are best learned via application. So, looking at the following equation. So again, here's our chemical reaction. Is this reaction balanced? And yes, this may seem like a repeat, but there's a critical distinction that I've provided in the following equation. And as students are beginning to type in the chat frantically, you're correct. This equation's not balanced. So I have 1 carbon and 1 oxygen in carbon monoxide. I have 2 oxygens in oxygen, and I have 1 carbon and 2 oxygens in carbon dioxide. So, pretending that we can cheat, what fraction would we guess to give us 1 oxygen, so that way we'd have 2 oxygens total on each side? What fraction would we guess for this isolated element of O2? What fraction would we guess? 1/2, exactly right. Okay, now that we have our fraction of 1/2, we multiply all of our coefficients by a whole number. And what whole number should we choose? What whole number should we choose to get rid of this fraction? What should we multiply all of our coefficients by? If we use this half notation shortcut, our denominator is 2, so we're going to multiply everything by 2. That in turn gives us 2 carbon monoxide gas plus oxygen gas leads to 2 CO2 gas. So now that we have a balanced equation, we can actually proceed with this problem. Notice, it seems like a very subtle, easy thing to do. Just, oh, the equation's balanced, let's balance it. But the act of just being attentive to whether or not your equation's balanced is critical in this chapter. Okay, so now let's answer the question, how many moles of oxygen are required to completely react with 5 moles of carbon monoxide? Okay, so we're going from moles of carbon monoxide to moles of oxygen. So we have 5.0 moles of carbon monoxide, and reading off from our coefficients, we have 1 mole of oxygen per 2 mole of carbon monoxide, which gives us 2.5 moles of oxygen. We've done this conversion before in an earlier example. Okay, let's try to answer the question now. How many moles of carbon dioxide are produced by complete reaction of 3.5 moles of oxygen? Okay, this time we're going from moles of oxygen to moles of carbon dioxide. If we have 3.5 moles of oxygen, we know that we have 2 moles of carbon dioxide per 1 mole of oxygen, and that in turn gives us 7 moles of carbon dioxide. Does this example make sense to everyone? So we're used to doing these mole to mole conversions, but this time we always have to check, do we have a balanced equation? So as I don't see any questions in the chat, let's keep going and let's work on the following example via Canvas quiz 6.7, or you can submit your responses in the chat. So given the following equation, notice it's not necessarily balanced. I'd like you to answer the following 2 questions. So how many moles of hydrogen are required to completely react with 2 moles of nitrogen? And how many moles of ammonia are produced by complete reaction of 1.5 moles of hydrogen? So I'm going to pan up so you can see the equation. And don't be shy to submit your responses via Canvas quiz 6.7. Oh, someone's using the annotate feature. Oh, I can clear it. You're welcome to try and share your solution using the annotate feature if you want to share your proposed solution that way. I'd be no, don't be sorry at all. You're more than welcome to try to showcase your solution using the annotate feature if you'd prefer. In fact, I'd encourage it. I was just not expecting it, since I didn't show students how to use that feature. But it's great for classes like organic, or when we get to structure drawing, we'll definitely discuss how to use that feature. And you're more than welcome to write your solution as well in this interface, and I'd be happy to look it over, and it would be a great discussion tool. So however you want to submit your solution in the chat, verbally, via Canvas, or even using the annotate tool. So for the message that I just received on the chat for the balance equation, one thing I would check is I would check the number of hydrogen and nitrogen atoms on each side. And I would just check to make sure that there are equal numbers of atoms on each side. You don't always have to have a coefficient that's different than 1 in front of your species. Sometimes you don't need to change the coefficient at all for some of the species in your chemical equation. So let's keep working through this example. We'll spend about 5 minutes in total on this example. In about another 2 minutes to a minute and a half, we'll go through and we'll balance the equation just to make sure that we can actually leverage our balanced equation to perform calculations. So we're reinforcing the skill of balancing equations, and then we're applying our balanced equation to stoichiometry problems. And checking Canvas, we have a pool of reasonable responses so far. So to help everyone out with the first aspect in terms of balancing this equation, so we have 2 nitrogens on the left, 2 hydrogens on the left, and 1 nitrogen and 3 hydrogens on the right. So to balance hydrogen, I'm going to use the least common multiple method. So we move the number of hydrogen atoms into the opposite species reaction coefficient. And that gives us N2 plus 3H2 leads to 2NH3. So we have 2 nitrogens and 6 hydrogens on the left, and we have 2 nitrogens and 6 hydrogens on the right. So now we have our balanced equation at play. So now let's take a few minutes and let's try to compute the moles of hydrogen required to completely react with 2 moles of nitrogen. And make sure to double check your reaction coefficients when you're making your mole to mole ratio. And we'll discuss this example in about another 2 to 3 minutes. So now that we have the chemical formula, we can apply our balanced equation to perform the following 2 mole to mole conversions. And the response I see in the chat looks perfect so far. No, the responses on the chat is perfectly fine. Yep, there are no issues with that response. Yep, everything looks fine in terms of your calculations. So checking to see how the class is doing. Everyone's pretty fast at responding for this. Let's try to get a few more responses and we'll discuss in about another minute. And if you have any questions at all, don't hesitate to ask them in the chat or verbally. And the responses I see in the chat so far look perfect. So let's discuss this example in about another 30 seconds. Okay, so let's discuss this example. So starting off, we're trying to go from the moles of nitrogen to the moles of hydrogen. So we have 2.0 moles of nitrogen. And we know that we have 3 moles of hydrogen required to react with every 1 mole of nitrogen. And that in turn gives us 6.0 moles of hydrogen. Perfect. Looking at our next example, we're trying to go from moles of hydrogen to moles of ammonia. We have 1.5 moles of hydrogen. And thinking about our moles of ammonia per mole of hydrogen, looking at our chemical equation, we see we have 2 moles of ammonia for every 3 moles of hydrogen. And that in turn gives us 1.0 moles of ammonia. Does this example make sense to everyone so far? Does this example make sense to everyone so far? Okay, so let's continue on now. And let's try to do a problem in which we have to do some mass conversions in addition to mole conversions. So given the following equation, and let's ask ourselves once again, is this equation balanced? Is this equation balanced? Is this equation balanced? No, it's not. We have 2 hydrogens and 1 sulfur on the left. We have 2 oxygens on the left. We have 2 hydrogens, 1 sulfur, and 4 oxygens on the right. So then, what coefficient do we need in front of oxygen? What coefficient do we need in front of oxygen to give us the 4 oxygens on each side? What coefficient? 2 times what would give us 4? 2 times what would give us 4? 2, yep. Okay, perfect. So now that we have our balanced equation in place and ready to go, we're asked how many grams of hydrogen sulfide are required to completely react with 5.5 moles of oxygen. Okay, So we're going from moles of oxygen, and our end goal is grams of hydrogen sulfide. So what is our intermediate stepping stone? What are our intermediate stepping stone? What units are we going to go through in this problem? What units are we going to go through? We're going from moles of oxygen, and we want to get to grams of hydrogen sulfide. Moles of hydrogen sulfide, exactly right. I always like to think about things in terms of the units. So if we have 5.5 moles of oxygen, my first question, if we're going to moles of hydrogen sulfide will be on top, moles of oxygen will be on the bottom, and how many moles of hydrogen sulfide do we need per mole of oxygen? What's our mole to mole ratio? What is our mole to mole ratio? 1 to 2, okay? Next, we need to figure out how many grams of hydrogen sulfide are present in 1 mole. So to do that, we're going to do a quick molar mass calculation. So we have 1 gram per mole for hydrogen, and we have 2 hydrogens. We have 32 gram per mole for sulfur times 1 mole, and that gives us 34 gram per mole. Okay, so now all we have to do is punch that into our calculator. And that in turn gives us a total mass of hydrogen sulfide of 93.5 grams, which we round to 94 grams of hydrogen sulfide. Does this example make sense to everyone? Any questions on this example? Okay, so continuing on, we're asked to calculate how many grams of sulfuric acid are produced by complete reaction of 10 grams of hydrogen sulfide. So we're asked to go from grams of hydrogen sulfide, and we're going to end with grams of sulfuric acid. So how do we relate these two chemical species? What units are we going to go through? What units allows us to relate the quantities of reactant and product? Moles, exactly right. So we're going from grams of hydrogen sulfide to moles of hydrogen sulfide to moles of sulfuric acid. Okay. So now that we have 10.0 grams of hydrogen sulfide, we know that in 1 mole of hydrogen sulfide, we have 34 grams. We already did that calculation for the molar mass. Now, and this is the important part, at least from a stoichiometry perspective, how many moles of sulfuric acid are produced per mole of hydrogen sulfide? So looking at our equation, what is the ratio of sulfuric acid to hydrogen sulfide? What is our mole to mole ratio? What is our mole to mole ratio? 1 to 1. So we have 1 mole of sulfuric acid per 1 mole of hydrogen sulfide. Okay, and then we need to figure out how many grams of sulfuric acid are present in 1 mole. So looking at the molar mass, we have 1 gram per mole times 2 plus 32 gram per mole times 1 plus 16 gram per mole times 4. So that in turn gives us 98 gram per mole. Okay, so punching this all into our calculator. So punching this into our calculator, that would give us 28.8 grams of sulfuric acid. Any questions on these examples? Any question on these examples? If not, what we'll do is we'll apply what we've learned in these examples and work on the following problem. And you can submit your responses via Canvas quiz 6.7.1 in the chat or verbally. And again, don't be shy to ask questions. So I'm going to pan down. Note there are 2 questions as this problem in this problem in your notes, but I'll set up so you can see the equation and the first problem. And don't be shy to submit your questions and proposed responses via Canvas or in the chat. And we'll discuss this example in about 5 minutes, but in about 2 minutes, we'll balance the equation. Just so that way, if you're not comfortable with balancing just quite yet, we'll get some more practice and clarity on that. So that way, when you try to apply your balanced equation, you have a balanced equation that is correct. This is Canvas quiz 6.7.1. And don't be shy to submit your responses, or you can submit your responses in the chat and I'd be happy to provide feedback. So we'll discuss our balanced equation in about 2 to 3 minutes, but you're welcome to submit your responses for both parts of this exercise in the chat or via Canvas. And we'll discuss the balanced equation in about another 1 to 2 minutes. Okay, so let's balance the equation. So on the left, we have 1 aluminum and 2 chlorines. On the right, we have 1 aluminum and 3 chlorines. Okay, so to balance out chlorine, we're going to use the least common multiple rule, and that gives us aluminum solid plus 3 chlorine leads to 2 aluminum chloride. Oops, that should be a solid. Okay, now that we have 2 aluminums on the right, we need 2 aluminums on the left. And now our equation is fully balanced. So let's take another 3 to 4 minutes and focus on completing the calculations for this problem. And just to comment on one of the responses I received in the chat, the responses look quite good so far. Yep, all the responses I see in the chat so far look perfect. Let's try to get a few more responses, and I'd like to see about the majority of the class have a submitted response either in the chat or via Canvas, just so that way I can make sure everyone in the class is comfortable with this material. And then we'll discuss this example in about 3 minutes, and we'll finish off these 2 problems. And the responses I see in the chat so far look quite good. We'll discuss this example in about another minute and a half. Checking Canvas in the chat. I'd like to get a few more responses just to give everyone an opportunity to receive feedback and compare their proposed solution to the instructor solution. Okay, so let's discuss this example. So we're asked how many grams of aluminum are needed to completely react with 70 grams of chlorine. So we're going from grams of chlorine to grams of aluminum. And again, as the central theme for this chapter, in order to go from grams of one species in the chemical reaction to grams of another species in the chemical reaction, what units do we go through? What are our intermediate units? What units are we going through as a stepping stone? What units are we going through? Moles, yep. So we're going from grams of chlorine to moles of chlorine, and moles of chlorine to moles of aluminum. Okay, so now that we have this setup at play, we know that from 70.0 grams of chlorine, we know that in 1 mole of chlorine, we have 35.45 times 2 grams. We know, looking at our chemical equation now, how many moles of aluminum are required per mole of chlorine? What's our mole to mole ratio of aluminum to chlorine? What's our mole to mole ratio? Two to three. Yep, we have 2 moles of aluminum per 3 moles of chlorine. And then we know that we have 27 grams of aluminum per 1 mole of aluminum. And if we punch that into our calculator, that in turn gives us 17.8 grams of aluminum. Okay, so let's take a look at another example. We're asked how many grams of aluminum chloride are produced by complete reaction of 81 grams of aluminum. So we're going from grams of aluminum to moles of aluminum to moles of aluminum chloride to grams of aluminum chloride. So we know that if we have 81 grams of aluminum in 1 mole of aluminum, we have 27 grams. Now my question is, how many moles of aluminum chloride do we produce per mole of aluminum consumed? What's our mole to mole ratio? 2 to 2, yep. Okay, and now we have to look at how many grams of aluminum chloride are present in 1 mole. So let's do a quick sidebar molar mass calculation. So we have 27 gram per mole, 27 gram per mole times 1 plus 35.45 gram per mole times 3. Okay, punching that into our calculator, we get 133.35. Okay. So now let's punch this entire calculation into our calculator. And that in turn gives us a mass of aluminum chloride of 400 grams. That we write as 4.0 times 10 to the second grams of aluminum chloride. Any questions on this example? Okay, so let's continue on now, and Let's look at another example. This time we're asked to perform stoichiometry calculations when we have a word form of our chemical equation. So we're asked to write and balance the chemical equation for the following reaction. So hydrogen peroxide decomposes to yield oxygen gas and liquid water. Okay, so hydrogen peroxide is H2O2. The to yield says I have to draw an arrow. Oxygen gas is O2 gas. And water is H2O liquid. Now, checking to see if my equation is balanced, I have 2 hydrogens and 2 oxygens on the left. I have 2 oxygens from oxygen, 1 oxygen from water, and 2 hydrogens from water. So ideally, instead of 3 oxygens total on the left, instead of 3 oxygens total on the right, I want 2. So then we can use half notation because we have an isolated element. So what fraction times 2 would give us the 1 oxygen atom that we need? What fraction times 2 would give us 1? Again, half notation is good because we have an isolated element in this case. So what coefficient should we have in front of oxygen? What fraction should we guess to give us 1 oxygen atom? What times 2 would give us 1? And you can guess a fraction in this case. 1/2 seems exactly right. Okay, so now that we have that set up, we don't have a full balanced equation just yet, so we're going to have to multiply all of our coefficients by our denominator of 2 to give us our fully balanced chemical equation. So we have 2H2O2 leads to O2 gas plus 2H2O liquid. So now that we have a balanced chemical equation, we can execute on solving this problem. So we're asked first, how many moles of liquid water are produced when 5 moles of hydrogen peroxide decomposes? So we're going from moles of hydrogen peroxide to moles of water. So we have 5.00 moles of hydrogen peroxide. And we know, looking at our chemical equation, how many moles of water do we have per mole of hydrogen peroxide? What is our mole to mole ratio? Two to 2, yep. And that in turn gives us 5.00 moles of water. Okay, so let's do another example. So we're next asked. Okay, perfect. So we're all set for this example. The only thing that's new about these sorts of problems is that you have to write the chemical equation from the word phrase. Okay, so let's continue on now. And let's try to apply what we've learned to the following example. We're asked to write out and balance the chemical equation, and you can submit your responses verbally or via Canvas quiz 6.7.2. And we'll discuss this example. First, we'll discuss the chemical equation in about 3 minutes, and then we'll discuss the rest of this problem. So the 2 parts for this problem in approximately another 3 minutes. So don't be shy to submit your responses via Canvas or in the chat, and we'll discuss momentarily. And the responses I'm seeing in the chat so far look good. We'll discuss our balanced chemical equation in about another minute and a half. Okay, so let's discuss balancing and writing out this equation. So magnesium metal is just magnesium solid. Nitrogen gas is N2 gas. Magnesium nitride, so magnesium adopts a 2+ charge. Nitride is a 3- charge. We cross our charges, that gives us Mg3, N2 solid. Okay, now this equation clearly is not balanced. So just looking at this equation, we have 1 magnesium on the left, we have 2 nitrogens on the left, and we have 3 magnesiums and 2 nitrogens on the right. So what coefficient do we guess for magnesium to give us 3 magnesium atoms on each side? What coefficient do we guess for magnesium? 1 times what would give us 3? 1 times what would give us 3? What coefficient do we need for magnesium? 3. Yep. So rewriting our balanced equation, we have 3 magnesium solid plus nitrogen gas leads to magnesium nitride solid. Okay, so continuing on with this idea, we're asked to calculate the moles of magnesium nitride formed from a complete reaction of 10 moles of magnesium. So we're going from moles of magnesium to moles of magnesium nitride. Okay. So if we have 10.0 moles of magnesium, how many moles of magnesium nitride do we make per how many moles of magnesium? What's our mole to mole ratio? What's our mole to mole ratio? One to 3, exactly right. Okay, so punching that into our calculator, that gives us 3.33 moles of magnesium nitride. Okay, so let's look at the next part of this problem. We're asked to figure out the moles of nitrogen consumed when 10 moles of magnesium reacts. So we're going from moles of magnesium to moles of nitrogen. So we have 10.0 moles of magnesium. And our goal is to figure out, and looking at our chemical equation, how many moles of nitrogen are required per how many moles of magnesium. What's our ratio of nitrogen to magnesium? What's our mole to mole ratio of nitrogen to magnesium?
1, 2, 3.
Yeah, exactly right. And that in turn gives us 3.33 moles of nitrogen. Perfect. Any questions on this example? The responses I've seen in the chat and via Canvas seem perfect so far. So let's keep going now. So let's do another guided example again where we have to write a formula from the word expression. And this time we're doing calculations involving masses. So carbon monoxide gas, that's CO gas, reacts with hydrogen, which is H2, to produce liquid methanol. So methanol is CH3OH. Okay, so now filling in our coefficients. So filling in our coefficients, we see we have 4 hydrogens, 1 carbon, and 1 oxygen on the left. Sorry, on the right. And we have 1 carbon, 1 oxygen, and 2 hydrogens on the left. So 2 times what would give us our needed 4 hydrogens? What coefficient do we guess for hydrogen? What coefficient do we need for hydrogen? 2, yep, there we go. So now we have our complete balanced chemical equation, and now we're ready to calculate the mass of methanol produced when 28 grams of carbon monoxide reacts. So we're going from grams of carbon monoxide to moles of carbon monoxide, to moles of methanol, to grams of methanol. Okay, so if we have 28 grams of carbon monoxide, we know in 1 mole of carbon monoxide, we have 28 grams. Looking at our mole to mole ratio, how many moles of methanol do we have per mole of carbon monoxide? What's our mole to mole ratio in this case?
One to one.
Yep, exactly right, 1 to 1. And then finally, looking at the grams of methanol per mole, we're going to need to calculate the molar mass per that. So let's do that. So calculating the molar mass really quickly, we have 12 gram per mole plus 1 gram per mole times 4 plus 16 gram per mole. That gives us a molar mass of 32 gram per mole. So punching this into our calculator now, we have 28 over 28 times 32, and that in turn gives us 32 grams of methanol produced. Okay, let's keep going with this. We're asked to calculate the mass of hydrogen required for a complete reaction of 28 grams of carbon monoxide. So we're going from grams of carbon monoxide to moles of carbon monoxide to moles of hydrogen to grams of hydrogen. So we have 28 grams of carbon monoxide times 1 mole of carbon monoxide per 28 grams. And now for the critical part. How many moles of hydrogen are required per mole of carbon monoxide? So looking at our chemical equation, what is our mole to mole ratio of hydrogen to carbon monoxide? And I already see students typing in the chat that it's a 2 to 1 ratio, and that's exactly right. And now how many grams of hydrogen are present in 1 mole of hydrogen? Notice it's H2, so it has a mass of 2 grams per mole. And that in turn gives us 4 grams of hydrogen. Any questions in this example? Any questions for this example? So let's try to apply what we've learned to another example. And this time let's look at Canvas Quiz 6.7.3. So you're asked to write and balance the chemical equation and then complete calculations using stoichiometry based on that chemical equation. So don't be shy to submit your responses via Canvas Quiz 6.7.3 or via the chat. And we'll discuss the balanced equation in about 2 to 3 minutes, and we'll discuss the entire problem in about 5 minutes. But first things first, we need a written, balanced chemical equation. And just as a reminder, this problem has 2 stoichiometry portions. The second part is right here. Okay, so we'll discuss the balanced chemical equation in about 2 minutes. And don't be shy to submit your responses via Canvas or in the chat. Okay, so let's focus on balancing this chemical equation. I already see some students have gone ahead and completed the stoichiometry part of this problem, so it's quite encouraging to see. So first, aluminum, so it's Al solid, reacts with oxygen gas, so O2 gas, to yield aluminum oxide, which is Al2O3. Okay, so looking at this equation, we can clearly see that it's not quite balanced. So we're going to utilize the least common multiple method. We have 2 oxygens on the left. We have 3 oxygens on the right. Let's swap our coefficients. That gives us 3 and 2. So now that we have 4 aluminum and 6 oxygens on the right, 6 oxygens on the left, and 1 aluminum on the left, what coefficient do we need to get 4 aluminums on each side of our chemical equation? How many aluminums do we need to get 4? What coefficient do we need? 1 times what would give us 4? What coefficient do we need for aluminum? 4, yep. Okay, so now that we have that set up, we're asked to calculate the mass of oxygen needed to completely react with 54 grams of aluminum. Okay, so we have our balanced equation right here. So then we're going from grams of aluminum. Again, we're always going through moles. We're going to moles of aluminum, to moles of oxygen, to grams of oxygen. Okay, so starting with 54 grams of aluminum, we know that in 1 mole of aluminum, we have 27 grams. We also know that we have how many moles of oxygen per mole of aluminum. What's our mole to mole ratio of oxygen to aluminum? What's our mole to mole ratio of oxygen to aluminum? What was that?
3 to 4.
3 to 4, exactly right. And in terms of grams of oxygen in 1 mole of oxygen, we know that we have 32 grams of oxygen per mole. So if we punch that into our calculator, we have 54 over 27 times 3 over 4 times 32. And that in turn gives us 48 grams of oxygen. Perfect. So let's continue on with these examples, and let's talk next about how to calculate the mass of aluminum oxide produced from the same reaction. So we have 54 grams of aluminum, and we're trying to go to moles of aluminum, but this time we're going to moles of aluminum oxide and grams of aluminum oxide. So now that we have our unit conversion map established, all we have to do is execute on that. In 1 mole of aluminum, we have 27 grams. My question to all of you is, how many moles of aluminum oxide do we have per mole of aluminum? What's our mole to mole ratio of aluminum oxide to aluminum? What's our mole to mole ratio? 2 to 4, exactly right. We have 2 moles of aluminum oxide per every 4 moles of aluminum. And then looking at the molar mass of aluminum oxide. So looking at the molar mass, we have 27 gram per mole times 2 plus 16 gram per mole times 3. That in turn gives us a molar mass of 102 gram per mole. If we punch this entire calculation into our calculator, get 54 over 27 times 1/2 times 102, we get 102 grams of aluminum oxide. Does this example make sense to everyone so far? Any questions so far? Okay, so let's keep going and let's try to apply what we've learned to the following example. We're looking at the reaction between aluminum and iron 3 oxide. I'd like you to write a balanced equation and then complete 2 stoichiometry sub-problems. Don't be shy to submit your responses via Canvas Quiz 6.7.4, and we will discuss this example. First, we'll discuss the balanced equation in about 2 to 3 minutes, and then we'll discuss the remainder of this problem in about 5 to 6 minutes. So let's work through this problem and make sure we're comfortable applying our skills at writing balanced chemical equations and utilizing that balanced equation for stoichiometry. And we'll discuss this example shortly. Again, don't be shy to ask questions in the chat or verbally, and don't be shy to submit your responses via Canvas. And we'll discuss the balanced chemical equation in about another minute to minute and a half. And the responses I see so far via Canvas, students have even gone ahead and are starting the stoichiometry portion already. Let's discuss next just our balanced equation. So aluminum has the formula of Al, iron 3 oxide. So we have Fe3 plus, O2 minus. We cross our charges and that gives us Fe2O3. Iron is Fe. Aluminum oxide is Al2O3 because we have aluminum 3 plus and O2 minus crossing our charges. Okay, so now from here, what we're going to do is we're going to balance our coefficients. We see we have 2 aluminums on the right, so we need 2 aluminums on the left. We have 2 irons on the left, so we need 2 irons on the right. So now we have a balanced chemical equation. So let's take a few additional minutes. And now that we have the balanced chemical equation, let's use that to solve these 2 stoichiometry problems. And we'll discuss this example in about 2 to 3 minutes now that we have our balanced equation. Let's try to get a few more responses via Canvas and in the chat. And the responses I see so far in the chat is great so far. And we'll discuss this example in about another minute and a half. Okay, so let's discuss this example. Looking at Canvas, we have a reasonable pool of responses so far. I greatly appreciate the class submitting their responses and any questions that they have, as it's invaluable at allowing me to provide constructive feedback. So we're asked how many grams of aluminum oxide are produced when 41.5 grams of aluminum react. So we're going from grams of aluminum to moles of aluminum to moles of aluminum oxide to grams of aluminum oxide. So we have 41.5 grams of aluminum. We know in 1 mole of aluminum, we have 27 grams. So in this equation, how many moles of aluminum oxide do we produce per mole of aluminum? What's our mole to mole ratio? What's our mole to mole ratio of aluminum oxide to aluminum? What's our mole to mole ratio? How many moles of aluminum oxide do we make per mole of aluminum? What's our mole to mole ratio? It's 1 to 2, exactly right. Then finally, we have 102 grams of aluminum oxide per every 1 mole of aluminum oxide. So punching that into our calculator, we have 41.5 over 27 times 1/2 times 102. And that in turn gives us 78.4 grams of aluminum oxide. Okay, let's keep going. Let's do another example. We're asked how many grams of iron are produced when 41.5 grams of aluminum react. So we have 41.5 grams of aluminum. We're going to go to moles of aluminum. Then using our equation, we'll go to moles of iron, followed by grams of iron. Okay, so we have 41.5 grams of aluminum. Just like before, in 1 mole of aluminum, we have 27 grams. Now let's look, how many moles of iron do we have per mole of aluminum? What is our mole to mole ratio of iron to aluminum? What is our mole to mole ratio of iron to aluminum? How many moles of iron do we make per mole of aluminum? What's our mole to mole ratio?
Two to two.
Yep, exactly right. So we have 2 moles of iron per every 2 moles of aluminum. And then finally, we know that we have 55.8 grams of iron per every 1 mole of iron. And if we punch this into our calculator, we get 41.5 over 27 times 2 over 2 times 55.8. And that gives us 85.8 grams of iron. Any questions on this example? Is everyone feeling more comfortable with stoichiometry, with writing balancing equations and using those equations in order to calculate the mass of product generated or reactant required? Okay, so let's look at an example that's pretty relevant. We've actually seen this reaction or a similar reaction in laboratory. So don't be shy to submit your responses via Canvas quiz 6.7.5 or in the chat, so that way you can receive immediate feedback. So I'd like you to write and balance a chemical equation for the following reaction. And then once you have the balanced equation established, I'd like you to perform some calculations based on that chemical reaction. And we'll discuss this example. First, the equation, as always, in about 2 to 3 minutes, and then the stoichiometry calculations in about another 3 minutes. and we'll discuss the balanced chemical equation in about another minute, just to give everyone enough time. Okay, so let's discuss the balanced chemical equation. So first and foremost, sodium hydroxide. We have sodium plus and OH minus. We cross the charges. That gives us NaOH. Sulfuric acid, it's derived from sulfate, H plus and SO4. We cross our charges. That gives us H2SO4, aqueous. Sodium sulfate follows the same logic. We cross our charges for sodium and sulfate, and that gives us Na2SO4. Water, we know that, H2O. Also known as dihydrogen monoxide if you are trying to get people to try to ban water because it has a weird sounding name outside of just water. Anyway, jokes aside, looking at our equation, it's clearly not balanced. So we see we have two sodiums on the right. So what coefficient do we need on the left? We have two sodiums on the right, so what coefficient do we need on the left? 2, right? Okay, perfect. Now, looking at our hydrogens in total, we have 4 hydrogens on the left. So what coefficient do we need for water? 2 hydrogens times what would give us 4 hydrogens? What coefficient do we need for water? 2, yep. Perfect. So now we have our complete balanced equation, and let's use this now for stoichiometry. So first things first, we're asked how many moles of potassium hydroxide. Oh, let's replace that with sodium hydroxide. So how many moles of sodium hydroxide are required to produce 3 moles of sodium sulfate? Okay. So we have 3 moles of sodium sulfate. And we know, look, how many moles of sodium hydroxide do we need per mole of sodium sulfate? What's our mole to mole ratio of sodium hydroxide to sodium sulfate? 2 to 1. We have 2 moles of sodium hydroxide per 1 mole of sodium sulfate, and that in turn gives us 6 moles of sodium hydroxide. Okay, let's look at this next part. How many grams of water would result from complete reaction of 1.2 grams of sulfuric acid? So we're going from grams of sulfuric acid, and as always, if we're using a chemical equation, we're going to go to moles of sulfuric acid, followed by moles of water, followed by grams of water. Okay, so if we have 1.2 grams of sulfuric acid, let's do just a quick sidebar calculation to figure out the molar mass. In 1 mole of sulfuric acid, we have 1 gram per mole times 2 plus 32 gram per mole. plus 16 gram per mole times 4. This feels very familiar. I think we've actually done this exact molar mass calculation before. That gives us a molar mass of 98 gram per mole. Now let's look at our chemical equation and figure out how many moles of water do we make per mole of sulfuric acid. What's our mole to mole ratio of water to sulfuric acid? What's our mole to mole ratio of water to sulfuric acid?
2 to 1.
2 to 1, exactly right, exactly right. So we have 2 moles of water per 1 mole of sulfuric acid, and then we know that we have 18 grams of water per 1 mole. So punching this into our calculator, we have 1.2 over 98 times 2 times 18, and that in turn gives us 0.44 grams of water. Does this example make sense to everyone? Any questions? So that's it for lecture for today. We'll take a 45-minute break and I will see everyone in laboratory at 12:45. So for a continuation of our lecture.